Hey everyone, and welcome to a deep dive into something really quite remarkable. It's spider silk.
Oh, it's fascinating stuff.
Yeah, and we're taking a look at this new article from Northwestern University,
Huh?
published in Science Advances. The title really kind of grabbed me.
Yeah?
It's Stronger Than Steel, Tougher Than Kevlar Spider Silk's Secret Finally Revealed.
Catchy.
I mean, it is catchy, but it's also like, wow. Stronger than steel, okay, tougher than Kevlar, but also stretchy like rubber.
Right, it's this incredible combination.
Yeah, it's like how?
And that's exactly what's baffled scientists for, decades, really.
Yeah.
This unique set of properties. How can something be so strong, so tough, and still stretch like that? It's like nature bending the rules of material science.
So it's not just like some hidden ingredient, it's actually the way the spider makes it.
That's the thing. It's all in the spinning process.
Uh-huh.
Picture this. You've got a spider carefully pulling the silk from its spinneret, using its legs to control the tension. It seems so simple,
Right.
right? But at a nanoscale, it's an incredible feat of engineering.
So the spider is basically like a tiny little engineer
Exactly.
stretching the silk as it spins it.
And that stretching, you wouldn't believe the impact it has.
I mean, does stretching really make that much of a difference?
Oh, absolutely. It all comes down to what happens at the molecular level.
Okay.
Imagine the silk proteins, these long, tangled strands, kind of like if you took a bowl of spaghetti.
Yeah.
Now, as the spider stretches, those strands align. They become tightly packed together, organized. It's almost like you're combing out that messy spaghetti into these neat, parallel lines.
Huh, so stretching brings order out of chaos.
It's a great way to put it.
But how does that make it so strong? I mean, how do we get from organized spaghetti to super strong material?
Well, that's where these tiny but incredibly powerful forces come in. They're called hydrogen bonds.
Okay.
You can think of them like little bridges forming between the protein strands, holding them together.
Okay.
And guess what? Stretching increases the number of those bonds.
Mm-hmm.
So you end up with this incredibly strong and resilient network, all thanks to those tiny bridges.
So more stretching, more bonds, more strength. I mean, it's simple when you put it like that.
Yeah, nature is elegant like that sometimes.
I'm looking at this article here, and it says researchers have actually managed to copy this process in the lab.
Yeah.
They're making artificial spider silk.
That's right. There's a team led by Fuzhong Zhang at Washington University in St. Louis.
Okay.
And they've been working with engineered microbes
Okay.
to produce spider silk proteins.
Yeah.
And by mimicking that spider stretching technique,
Mm-hmm.
they've created artificial fibers that are really getting close in terms of strength and toughness to the real deal, to natural spider silk.
So we're not just talking theory here, it's actually happening. But if spiders can do this so effortlessly, why has it been so hard for us to replicate? What are the challenges scientists face in trying to scale up production?
That's a great question. And it brings us to some of the really interesting intricacies of trying to translate this natural wonder into something that we can actually produce on a larger scale. It's a whole other challenge, and we'll definitely get into that in the next part of our deep dive.
Sounds good. Looking forward to it.
You know, spiders have had millions of years
Right.
to perfect this whole silk spinning process.
Yeah.
It really is this marvel of evolution,
It is.
like happening all within this tiny little organ, the spinneret,
Huh?
and replicating that
Yeah.
in a lab.
Yeah.
That's a whole other challenge.
So it's more than just like having the right ingredients.
Oh, yeah.
Like, what are some of the biggest roadblocks to making artificial spider silk in like large quantities?
Well, one of the really tricky things is controlling the alignment of those protein strands.
Right. Right. Like that neat parallel arrangement. like it
Exactly.
seems,
That's absolutely crucial for the
Yeah.
strength in the spider.
Right.
It just does this through this precise control of the tension and the spinning speed.
Yeah.
And to replicate that mechanically,
Yeah.
it's really complex.
It's like trying to recreate a master chef's dish.
Yeah.
It's just from the ingredient list.
Exactly. You're missing that finesse,
It's like, how did they?
that unspoken knowledge.
Yeah.
And Zhang's team, they've made incredible progress.
Right.
But now think about scaling that up
Yeah.
to produce industrial quantities of silk.
Right.
You need sophisticated equipment,
Yeah.
precise control over temperature, pressure,
Uh-huh.
deep understanding of protein chemistry.
So we're talking a pretty sophisticated operation.
Oh, yeah. It's a huge undertaking.
Yeah.
And that brings us to another challenge, cost.
Okay.
Right now, producing artificial spider silk in the lab,
Yeah.
it is quite expensive.
Okay.
So to make it commercially viable, we've got to find ways to make that process more efficient.
Uh-huh.
and affordable.
So we're trying to hit that,
That sweet spot.
sweet spot. Yeah.
Quality, scalability,
Affordability.
affordability, it's like the holy grail of material science.
It really is.
And there's this other aspect,
Okay.
which is tailoring the properties of the artificial silk for different uses.
Okay.
You might need one type of silk that's super strong
Yeah.
for building things,
Right.
but for medical use, you might want something that's more flexible
Right.
and compatible with the body.
So we can't just create like a one-size-fits-all spider silk.
Not quite. We've got to learn to fine-tune the production,
Right.
to manipulate those hydrogen bonds,
Right.
the protein alignment,
Uh-huh.
all these factors
What do you want?
to create silks with specific
It's
characteristics.
exciting, though.
It was a cutting-edge area of research.
To think that we could engineer silk for almost any purpose
That's impossible.
just by messing with those tiny little bonds and protein strands,
The possibilities are immense.
it really opens up a whole world of possibilities.
It does. And speaking of possibilities, why don't we step outside the lab for a second
Okay.
and explore some of the potential applications of spider silk in the real world across different industries?
All right.
Ready to take a glimpse into the future?
Let's do it. All right. Let's hear it. What kind of future are we talking about?
Okay, well, let's start with something that we can all relate to. Clothes.
Okay.
Imagine fabrics, light as a feather, but tougher than denim, breathable,
Okay.
maybe even waterproof, all thanks to spider silk.
So like next level athleisure wear.
Exactly.
I mean, I'd wear that. What else? What else?
Okay, think high-performance athletic wear that helps you recover faster. Or protective gear for firefighters or soldiers that's lighter and stronger than anything we have now.
Okay, so we're talking clothes that can like make you feel like a superhero.
In a way, yes.
But what about beyond fashion? Where else could this spider silk make a real difference?
Think bigger, like construction.
Yep.
Imagine using spider silk composites to reinforce concrete. You could have buildings that are lighter, stronger,
Yeah.
more resistant to things like earthquakes.
Wow, that would be a game changer. I
Yeah.
mean, making cities safer and more sustainable.
Absolutely.
That's huge. What else?
Well, let's not forget medicine.
Okay.
Picture this. Surgical sutures
Yeah.
that are not only stronger and more flexible than what we use now, but they're also biodegradable.
What?
Yeah, they just dissolve after they've done their job.
No way.
So you wouldn't need as many follow-up surgeries
Yeah.
and less scarring.
That's straight out of a sci-fi movie.
I know, right? But it's becoming a reality.
It's really happening.
And there's more. Spider silk has these antimicrobial properties,
Oh.
which means you could use it for things like advanced wound dressings.
Okay.
They could help heal faster and prevent infections.
So we're talking next level medical tech.
Yeah.
And it's all inspired by what? A spider web?
Nature is full of amazing solutions.
It really is. It's like it was right there in front of us this whole time.
Exactly. And it doesn't stop there.
Right.
The aerospace industry, they could use spider silk to create lighter and more fuel-efficient parts for aircraft.
So planes that could fly further with less environmental impact.
Exactly.
It's mind-blowing.
It is, isn't it?
The potential of this one material is incredible. Like spider silk could revolutionize so many industries.
It's a real testament to the power of biomimicry,
Yeah.
looking to nature for answers.
Yeah.
It pushes the boundaries of what we thought was possible.
It's a reminder that the best solutions are sometimes right there in front of us.
Okay.
We just have to look for them. And who knew this delicate little spider web
Right.
could hold the key to a better future?
A more sustainable future, a more technologically advanced future.
Absolutely.
It really makes you think.
It does. So the next time I see a spider web, I'm not going to think, ooh,
Yeah.
I'm going to think about all this incredible potential.
That blueprint for a more resilient future.
Exactly. Well, I think it's safe to say that this deep dive into spider silk has left us with a sense of awe and a whole lot of hope for the future.
It's incredible to think that something so small could have such a huge impact.
Well, thanks for joining us on this journey into the world of spider silk. And as always, keep exploring, stay curious, and we'll see you next time on The Deep Dive.